Hi, so I wanted to do a bit about serial decoding and bus modes on this new RTB2004 scope, partly because it's something I use a lot and have got some sort of significant opinions about, and also there's very little information in the documentation that Rohde Schwarz have got on their website at the moment. There's sort of really almost nothing, so sort of quite a few queries that people have raised that I'll see if I can answer. Before that, just a couple of minor things on grids and also a small bug that I found. All scopes have got a grid display. What's special about this? But there's a few interesting things they've done on this. The first is that because they've got a nice high resolution screen, they can actually add these little annotations. So it'll actually tell you, for example, on the horizontal grid, this is the amount of time since the trigger event. So if I sort of center that, so that's our 0 trigger event, but basically it means it tells you what that grid line represents in terms of time, which obviously that can be useful, for example, if you sort of zoom right in, and so you don't have to sort of zoom out and look at cursors. You can immediately see, okay, that grid line, that's 70.5128 microseconds. I think that's a really handy feature, which is really being enabled by the fact they've got a high-res display. And they do the same thing on the vertical axis as well. So again, whatever the voltage offset, that grid line will always be that that voltage. I think that's a neat little facility. You can turn these off if you don't like them. It is optional, but they're small enough to I don't think they're particularly offensive. And if you change channels on the vertical ones, the annotations are shown in the colour of the channel. So obviously you might have different Y settings on different channels, so it will just show you the Y setting for the channel that's currently selected, colour coded. The other really handy thing, which I've not seen on any other scope, which certainly I've had a need for in the past and would have found very useful, is what you can do is you can tell it to track. Now what this does, this basically locks the grid to the trigger position. So for example here, if I just zero that, so this is our trigger position. You now notice that as we scroll on the waveform, the grid moves with it. Now what that can be useful for is if you're trying to sort of reverse engineer or do some decoding of a protocol that you don't have a decoder for. So for example, what you can do is use the fine time-based controls to get, so let's say this is some weird communications protocol that we don't understand. We could, for example, let's say for example it's Manchester code. Obviously this is actually UART data, but let's pretend it's Manchester code. We could adjust it to get one grid space per bit cell, and then because the grid moves, our grid is now acting as a bit cell marker. So if you're trying to sort of manually decode protocols, and this is, it's a really simple thing, but that can be really, really useful for doing that sort of thing. It means you've always got your reference positions, and as well as obviously on the bottom you've actually got the absolute timing as well. But the fact that you can draw a grid and then track as you scroll through and look at the waveform, that I think that's actually for a few very specific instances, that's extremely useful. Okay, there's one minor issue I found, which I'm pretty sure is actually a bug. Obviously you've got these nice sort of scrolling gestures. You can sort of expand and contract the waveform, and it behaves pretty much like you expect. So for example, if I expand around here, it stretches out from where I'm expanding it from. So again here it stretches it outwards, then I can go in and expand it. But there does appear to be an issue. Now this is the sort of the default mode on most scopes, in that the timing reference is at the centre, but I very rarely actually use that. Unfortunately, a lot of the lower end scopes don't really seem to sort of understand how useful this is. Most of the time on a scope, what you're interested in is what's happening after the trigger and not before it. Now of course what you can do is you can obviously just sort of scroll back and move your reference point to the left, but the problem is if you then start changing the time base, that position disappears. So this scope, and certainly the Keysight ones, I don't know how common this is on other scopes, but certainly a lot of low-end scopes I found don't let you do this, is you can set the reference point to be either the left or the middle or the right. So now what it's doing is, this is now saying that this is our trigger point. So because we're interested in what's happening after the trigger, we've now get most of the screen dedicated to that. And obviously now as we zoom in, it always stays referenced around that. So 95% of the time I use a scope, I use it in this mode. However, it seems they've messed up the gesture scrolling, in that the gesture expansion expands around the wrong point. Now I'd expect to go here and expand it this way, but if you look at what actually happens, it's expanding around the wrong point. So likewise here, if I go here, I expect this to all move that away. But again, it's expanding around a different point, and I think what it's actually doing, I think it's actually not applying this offset to where you put your fingers. So if I sort of go from the centre, if I just move that so that the trace starts at the trigger point, if I expand around the centre, that's actually expanding around that trigger point. So I think they've just forgotten to include that reference point in their position calculations when you try and expand a trigger. So I'm sure that's something that's very trivial for them to fix. Similarly, if you set it to trigger on the right, so for example you've got a situation where you're triggering at the end of an event, almost any expansion here should actually just make this fly off the right hand side of the screen, but actually it's actually pulling it in. So again, I think it's just using that wrong reference point, but so I'm sure that's something they can fix easily enough. There is another issue, which is at least a documentation problem for the serial decode. Depending on which documentation you read, on the product data sheet of the whole scope it says that the serial decode will go up to 32 megabaud. On the data sheet for the actual option it says it does up to 12 megabaud, but actually when you try and adjust it, it stops at 3. Now I'm guessing that those errors may have been sort of typos from a carryover from other products, but I think 3 is too low a limit. I routinely use 4 megabaud, occasionally 6 megabaud for things. Now I understand there may be issues in terms of granularity. So for example on the Keysight it has adjustable baud rate anything up to 8 megabaud, but it also has a 10 meg fixed rate as well. So even if it's sort of adjustable up to 3 and then maybe fixed rates at say 4, 5, 6, perhaps 8, that will be an improvement. I think 3 megabaud is a bit of a limitation, which considering the rest of the serial decode is actually really good. It's just unfortunate that it only goes up to 3 megabaud. Of course, when I was scrolling, this is going to fairly arbitrary figures, but you can just enter it. Like if, for example, if I wanted to do say 2.67 megabaud, it will let me do that. Incidentally, one minor thing which Keysight do slightly better is that when it pops up a numeric entry thing, it actually does a little bit of filtering. So for example here, I'm popping up the baud rate thing, but it's still giving me values that don't really make any sense. Whereas on the Keysight MSOX3104T, when it pops up a keyboard to let you enter values, it actually doesn't give you any of the multipliers that don't make sense for that input, which is just a minor thing. One nice thing this does do though, which the Keysight doesn't, it actually does give you the limits. It actually says what the values of those, the values are of that location. And it's also got a calculator open. That's try to clear. So I can say 12 times 8. That's actually quite useful because occasionally, not so much for baud rates, but there are things like, for example, if you're entering, say, a hold-off time, it's actually quite handy just to be able to just add a few values together. There are a few serial protocol decode and trigger options on this. They are options, and I think they're actually rather expensive. They're slightly more expensive than the Keysight 2000X series, but also I think, an oscilloscope is a general purpose instrument, and pretty much everything these days has a serial bus of some sort in it. So I think to consider serial decode and trigger as optional, I think is really getting a bit dated. And I think it really is about time manufacturers just included it as standard. We're seeing particularly things like FFTs as standard. No, I don't think anybody charges for that as an option. And to be honest, certainly in my case, I use serial decode far more than FFT. So I think really it is about time that manufacturers start including those as standard on their products, especially on the higher end products. It may be the case that there are, they may well do bundle deals, or you might be able to sort of talk nicely to your distributor and get them to throw some options in. I don't know what the situation is on there, but I think it is, considering it is a very useful facility, but it's also something where pretty much anything you're going to poke a scope out is going to have serial in there. I think it's a little bit mean to not include that into what is really a general purpose instrument. So basically we've got 2 different decodes here available which are independently settable. So for example we could have UART and SPI. The other thing incidentally, as well as the serial decodes, it does have parallel bus modes, which I'll go into a bit later. And as far as I know, I think those are standard. I don't think those are options. So those allow you to link up a number of the parallel inputs on the, particularly on the MSO ports, to turn them into a bus. So for example you could say have 8 bits and it will then actually show you like hexadecimal values that appear on that bus. The bus decode is only for the MSO option. So if we look at the serial decodes, we've got SPI 2 and 3 wire, I2C, UART, CAN and LIN. UART's the one that I use most often. So we can do 2 decodes. So for example, I can set bus 1 as UART. I can also set bus 2 as UART, but for example, I could set that up as a different baud rate. Or I could say have transmit and receive data. This is one area where it differs from, for example, the Keysight, in that the Keysight UART decode always gives you 2 channels for transmit and receive. And on the 3000 series, which lets you have 2 decodes, you can actually have 2 pairs of UART decode. And for example, they can run at different baud rates. But having 2 buses means, for example, you can decode UART on one channel and SPI, or say I2C. So for example, let's say you've got a piece of kit where you send it a serial command and it reads something out from an I2C bus. You can then actually show both of those decodes simultaneously. And also having 2 UARTs at different baud rates can also be useful, because as I showed in another video recently, UART decode is a very useful general purpose debugging tool. So for example, you might have something that takes some data in from serial, but during, for example, your serial receive code, you might want to spit out some debug data, maybe at a higher baud rate. Let's say, for example, when you receive 1 byte, you might want to send, say, 3 bytes of debug data. So you could set up a second serial decode at a higher baud rate to show that debug information. Right, so let's take a look at the UART decode setup. Obviously we can select the source from any of the analog and digital channels, and we can also set the threshold. But one really neat feature is this find threshold, where it will just look at what's coming in and figure out the threshold by itself. That's just a nice little time saver. Obviously got the usual parity stop bits, baud rate, so we can either go from a list of predefined rates, which are all the standard ones, although this list is a little bit incomplete in that, it goes, for example, 115 to, it doesn't have 230 or 460 in there as standard rates, but you can enter a user defined rate up to 3 megabaud. And obviously for setting these, you can use the twiddly knob as well as entering them with the keypad. Now this is an interesting feature. Obviously with serial, it's not just about single bytes, it's about packets. So what this lets you do is tell it how long a delay after a byte represents the end of a packet. So generally you'll have a burst of data and a gap after it, and then you can then tell it how much idle time means it's the end of the packet rather than just a gap between bytes. Now this is actually really useful, except there's actually a bug that means this isn't actually quite as useful as it should be, but hopefully they'll fix that. But there's this is both used for display, but it's also used in the serial trigger mode, which I'll show you in a minute. But I've set, say, a 20 microsecond gap, so after it sees no data for 20 microseconds, it assumes, okay, that's the end of the frame. We'll treat that as a frame. So let's actually take a look at this on screen. Now, what we've got, obviously, we've got the actual data packet themselves, but we've also got these frame markers around the outside. And looking at the SPI mode, these markers are definitely supposed to show the beginning and the end of the frame, but they don't. They're actually framing around each byte. So, I mean, that's definitely not right. If we told it what a frame should be, then we should see the square brackets only around that whole packet, not between each byte. So that's definitely something they need to look at. They've done some quite clever stuff in terms of optimizing the screen layout here. Well, firstly, we can select the vertical position, so we can place that anywhere we want on the screen, but also we can place the height. Now that's quite good, obviously, if you've got a really crowded display with lots of other stuff going on. But there's actually another interesting thing they've done here. As we close down our scale, we can see it starts off saying data and then the value in hex, then it goes down to D, then it sort of basically, as we close down, it optimizes the use of the screens. We still see as much data for as long as we can, and then as soon as it can't display it, it just blanks it. I think if they sort out this framing issue, I think a lot of this space is actually being wasted by this square framing. I think if they sort that out, then we'll actually see a little bit more there. But there's another quite neat thing they've done, is if it's gone down too small, what you can then do is increase the height, so you can actually trade off vertical space usage to optimize the display. So, and again, as we now close this down, we can now see a lot more bytes in one go on the screen. So that's really nice. They've really thought out, how can we optimize this, so you can, the user can trade off the space. So and say, well, once they sort out this framing issue, that'd be nice, and we'll get a nice square frame around the whole packet to identify where one packet starts and one packet stops. The other interesting thing, you'll notice it's actually showing the digital data as a tiny little line above the decode data. Now you might think, well, why do you need that? Well, if you're looking at a bus, you generally, you don't necessarily actually need to have the actual waveform on screen, so we can turn that channel off. Oops. So we can turn that channel off. So now all we've got is the bus, because again, we might have other stuff in other channels. So, you know, if we've got a really packed out screen, we don't really want to waste it. We've got just this really small view of it. And I think that could be really handy just as a quick like reality check. So for example, if I, for example, just set the baud rate wrong, you know, we're starting to see, oh, you know, why is this data looking like rubbish? But you can actually, by looking at the data, you can see, oh, you know, the baud rate is obviously wrong. You've got some visibility of the actual data on the line, just to provide a little reality check. So I think that's quite a neat feature. You can turn that off. So if you don't want that, you just go into display setup and turn off the bits mode. The display format, you've got all the sort of usual stuff. You've got binary, decimal, and again, it's fairly clever in the way it sort of squeezes out on the display. It's even got octal. Does anybody use octal? Decimal, that's handy. Some decodes don't do decimal. I think the Keysight doesn't do decimal, and that one time that can be useful is when you're using it as a debug output. Sometimes, you know, you're sending some debug data out, and in certain cases it may make more sense to look at it in decimal than hex. It's also got ASCII, except here's another issue which I would say it's somewhere between a bug and an omission, in that it displays your ASCII characters quite nicely, but what it doesn't do is display non-printing characters. So for example, I'm actually sending a carriage return line feeding an 80 byte here, so I can sort of just scroll through all the formats. So you can see, for example, if I go to the end of the packet, we've got this OD OA 80, but if I flip to ASCII, it just shows blank, which, I mean, that's just stupid. It should say, I would say probably the best thing to do there would actually display it in hex. Obviously there are some standard ASCII non-printing characters like CRLF, whatever, but I think it might be, it should just maybe put it in brackets and hex. Or, I mean, I think because it's showing ASCII, just showing 2 hex digits wouldn't have any ambiguity, because normally you can clearly see it's 1 letter per byte, so having a 2-digit hex value in there I think would make total sense. Hopefully when they're looking at the framing issue they might fix that as well. Another nice thing they do is they explicitly decode break conditions. Break is basically when the data is still low during the stop bit time. The most common use of this is the DMX protocol that uses break as a starter frame marker. If you look at the same data on the Keysights, you see it does actually flag it as an error, but it's a little bit vague. It just says, oh, you know, I don't know why that is, and something red happened. Whereas, yeah, this makes everything a lot clearer. You can actually trigger on a break as well, which you can't do on the Keysight. Although in practice, you can trigger on you can use the pulse width trigger to effectively get the same functionality. But it's nice just to have that explicit option. The serial triggering is also fairly comprehensive. So if we set up a serial bus trigger, we've also got the same setup, so we can go in and set the serial stuff up here. And there's quite a few useful things we've got. So obviously you've got the traditional start bit, stop bit, framing error, and break. Actually, I wonder if that frame error actually is the equivalent of a break, or if that's actually a packet length error. But yeah, it's interesting. Although the display doesn't seem to do the framing right, the frame start does actually seem to figure out that that's the start of a frame. But so I think that's just an issue with the display rather than the trigger setup. But we can also do symbol end. So basically what that will do is let us trigger on the nth symbol. So if I go to 0, so again it's identified the packet, and if, for example, I can trigger it on say the 9th symbol in the packet, I think you can go up to about 4096 there, so that's quite nice. So you can actually trigger on a specific character in the packet. And again, on long packets it means you don't have to count. Let's say, for example, you're doing some debugging and you don't know whether you're actually twiddling the 23rd or the 24th byte. You can actually just say go to go to that byte there, and it will just read off which one's changing. Or for example, you can see a value that's changing and you want to quickly know exactly which byte within the packet it is. Again, you can just use this, and when it lines up with your trigger point, you know that's that's that byte. The other thing you could do is trigger on specific characters. Now, any symbol means a specific value at any position within the packet. So, for example, if I trigger on 49 hex, which is I, that's now triggering on this I. And if I change that to, say, 53, that should now trigger on the S. So again, we're now triggering on that S, so we can trigger on a specific character. What would be nice, I'd like to see, although you enter it in hex, which is fine, I'd like to see it actually display the ASCII as well. So if you're trying to trigger on alphanumeric, yeah, if I enter a value there Obviously I can, that's interesting. I can't use the twiddly knob to spin that up and down, which I'd quite like to be able to do. But the other thing is you can put an unknown in there as well, so you can trigger on a binary pattern. So again, you can trigger on sort of wildcarded values, and again that will be really handy if, for example, you're using serial debug. You could be, say, throwing out values depending on what your system's doing, say like perhaps a state machine state, and you can make it trigger when it enters a range of states, which is quite nice. And the other thing you can do with pattern is you can look for a specific value at a specific offset. So you can actually trigger on up to 4, so you can actually trigger on a sequence of 4 characters at any offset. What would be nice though is to have an option to trigger on an exclude trigger. So for example, trigger when the pattern does not match this. So for example, if you're looking for an error or glitch that you know, for example, you're normally sending a certain sequence of characters, it would be nice to say trigger whenever you see a sequence of characters which does not match this pattern. But so this is still, you know, way in advance of any other serial trigger that I've seen. It would just be nice if you go into this this level of detail. It'd be nice just to have the other case to trigger when it isn't doing something, because quite often that's the thing you're actually trying to track down. I think that's everything for the UART decode. I mean, feature-wise, it's certainly the most feature-rich serial decode I've seen on a scope in terms of UART decodes. A couple of minor issues, particularly this framing thing, and if you could do the framing, actually do it properly on screen. So hopefully they'll sort that out. But in terms of functionality, it's really good. But also the limitation on 3 mega board, that's something which I really hope they're going to take a look at, because I think that these days, 3 mega board, I regularly run RS485 buses at 4 and 6 mega board. So I don't know where that limitation has come from, and even if it's fine, if I can't do like 3 point something weird, if I can at least do 4.0, 5.0, maybe 6, that would be a really good compromise. And of course the decode still works. If you go into zoom mode, you can look at details, and it will decode both the zoomed and the unzoomed section. And the other thing we've got a bus table mode. We can actually pull up a table showing the packet. So for example, here we're seeing the actual timestamp on each byte received. It's actually showing these as individual frames, which is wrong. So presumably this will track, when it saw that timeout, it will then change that from 1 to 2, etc. We can go down, and then we can save these packets. So we can either show the time since our trigger reference point, or we can just show the time from frame to frame. Okay, let's take a look at the SPI decode. Now there's 2 modes. One is what they call SSPI, which I think is presumably simple SPI, which is where you have clock data and then just a timeout on the clock to do the framing. Again, you've got this nice fine threshold that will just figure out the thresholds, which is a real nice time saver. The word size goes up to 32 bits, which again, that's a slight improvement. The key site only goes up to 16. And so we've got this idle time, and again, instead of between bytes as in UART, this is now between clocks. So we can set up the value just to tell it what we regard as being a frame. So again, we've got this little display of the bits, and this is probably actually more useful in SPI, in that you've got several signals, and it's quite handy just to get this little display of what's actually happening on the bus if you don't want to use up screen space with the actual traces. So we've told it now that our idle time, this is set to 330 nanoseconds, so it's assuming that each one of these is a complete word, because we've told it this timeout. So it's now treating these as individual frames, and we can see these square frame markers. But if I increase that framing time to actually tell it that now this is a whole frame, we've told it there's a 3.6 microsecond timeout, so that it will assume the frame ends when it's seen nothing for 3.6 microseconds. We're now seeing it's treating this whole thing as a single frame. The other thing, again, I just noticed actually by accident when I was twiddling, if I set this to 16 bits, it's now saying, okay, we've got a good frame, but it's showing this in red because we've got the timeout and we haven't actually seen 16 bits. So it's actually telling us there's actually an error in this SPI data, which is, again, it's really neat. It's actually telling you that there's something not right with that data, because it hasn't got enough clocks before the frame timeout occurs. So I think this could be really useful for tracking down errors in all sorts of serial. Although it's called SPI decode, but there's lots of things where you just got like a clock and data, which could be driving almost anything, whether it's like display shift registers for LED drivers or all sorts of things. So this is quite a nice sort of fairly general purpose clock and data debug tool. Now it is only showing data in one direction, but of course we do have the 2 decodes, so we should in principle be able to set up a second decode to show data in the other direction. Most of the other options are pretty much the same as in UART. So for example, the trigger mode, we've got frame start, frame end, and serial patterns, yeah, very similar to what we had before. Trigger on specific bits. That's handy because quite often, for example, some LED drivers you have like fairly long streams of bits with configuration data in, so it can be handy just to trigger on a specific bit number without really treating it as being framed up into bytes. Yeah, I think there's something weird colour balance. My fingers are looking very yellow, but I assure you that's colour balance. I'm not turning yellow. And again, like, we can trigger on any particular bit in the stream as well. What would be nice, this whole thing takes up the whole screen. It would be nice to actually be able to see the data while we're doing this. Maybe if there's like a transparent mode for this menu, that'd be quite nice. And so just while I'm setting something up for SPI decode, one thing that I'm finding a little bit annoying on this scope is that to set a trigger hold off is a bit fiddlier than it needs to be. Firstly, the hold off is buried right at the bottom of this menu, so you have to sort of get to it. And then when you enter the time, obviously you can just type a value in. I can say 20 milliseconds or whatever. But if I want to adjust that manually using the knob, when you're adjusting with this knob, firstly, because it's a detented knob, it doesn't really have sort of the nice velocity sensing you get, for example, on the Keysight models. And it does have something like if you give it like a flick, it will actually flick, moving fairly big chunks. But one thing about hold off time specifically is quite often if you've got an unstable waveform, you sometimes actually want to adjust the hold off time until it gets stable, and that's where it's quite good to have a slightly sort of better control. But it feels like this one, if you move it slowly, you've got quite small sections, but because you pretty much have to flick it to get it to a bigger thing, you don't really have any control over it. Whereas if you've got a non-detented encoder, you've got a much better feel for the speed, so you can actually control it a bit better. It's just something I think I think that's one reason why you just don't, particularly for the the knob that controls lots of different things. I just don't think a detented knob is a good solution. Okay, now so we've now got serial SPI decode running on our. So we're now right. So we've got this set up now. As I say, we're reading data from an SPI flash chip. So we've got our chip select here, our clocks, our data into the chip. So this is the decode. That's the 03 command, and then we've got our address. So you can see we're reading from a couple of different addresses. If we wanted to, we could bunch that up into larger chunks. Let's just try that. So if we actually tell it that it's 32-bit. So we're now treating that part, these are 2 separate 32-bit words. And we see it's now framing these by chip select, because we're now using traditional SPI where we have a chip select signal. It's framing these according to the chip select and ignoring the actual timing. So that if you look on the configuration page, we now don't have a timeout, because we know now that chip select is what's defining our framing. And obviously we've got the options, like we can say whether the chip select's active high or low, clock is rising or falling edge, data's true or inverted, and whether our data bytes are MSB or LSB first. So again, that's flexible for things that may not actually be SPI, but they're just some serial bus that you want to get some insight into. Now let's see if we can actually set up a 4th channel so we can see our data coming out. This is our data coming out, but we're not currently decoding that. So let's see if we can set the 2nd channel up to do the decode on this data so we can see both sides of the transaction. The sort of slidey bits on the submenus, sometimes they catch you unawares. You're sort of trying to find something and don't quite realise where it is, and then you sort of notice this scroll bar and there's actually a bit off the bottom, which it's just really a case of familiarity, I think. So we go bus 2, SPI 3 wire, and we set this up the same. So chip select channel 1, clock channel 2, and data now on channel 4. 8-bit. So hopefully, and turn the decode on, and what we should now be able to see is both decodes. So that's our 2nd. If we just shuffle these analog channels up out the way a little bit. there, but we can select it, so I can just touch on that one, move it up and down, touch on that one, move it up and down, so that's fine. So yeah, so now what we're actually seeing, we've got these two separate serial SPI decodes. This one is decoding the data going into the chip, and this is the data that we're reading out of the chip here. So that is working pretty much as expected, and obviously you can adjust how much space this takes up on screen to effectively get, for example, if we turn off the little wibbly bit displays as well, we'll get pretty much what we'd expect. So if you go display setup, turn the bits off, and bus 1, display setup, turn the bits off. So here, so now we've got our pure SPI data being shown on screen. We've got our framing markers, so for example we could turn off chip select because we don't particularly need to see that. So now we've got our decodes. What it's doing, it's adjusting the width of these according to the width of the clock burst. So the reason it's showing these as really short bits is because it's scaling that according to the span of the clock on screen. So as we expand our scale, we see these sort of stretching out again. So yeah, that's giving us information as to how long our clock's lasting. But so yeah, the SPI decode, that seems to work pretty nicely. The spec on the option says up to 25 megabits per second, but so as we've seen a few errors in the UART spec, let's just see if we can actually test that to figure out what speed it'll actually go to. Okay, this is the only thing I could easily find that does fast SPI. This is running at 25 megabits SPI, and that does appear to be decoding okay, so at least that spec looks like it's correct. The only other frequency I can easily try is 50 megahertz, and it does actually appear to be working at 50 megahertz. Can't do a comprehensive test, but it does actually appear to be correctly decoding data with a fairly sort of dubious probing setup at 50 megahertz on SPI, which is in excess of their spec. So whether it would do it under all conditions, I don't know, but I would hope that if it's too fast, it will like do some red or something on here to tell me it's too fast. But that's quite nice that it will do that, because things like SPI flash can actually go at that sort of speed. So if you're pulling data really rapidly out of SPI flash, then that's potentially quite useful that it can run that fast. Let's take a quick look at I2C. You've got this board here. This is just continuously reading data out of a serial E2 prom. And so you can see it's nicely colour coded it. That's our write to the device address. That's our read from the device address. So it's sort of colour coded those, which is quite nice. If you sort of zoom, even if you zoom quite a long way out, you can still see some of that colour coding going on. And if you zoom right in, you can see it's actually split out. So it's showing this is our read write bit, this is our acknowledge bit, and it seems to be framing these as well. We've got these frame markers here and here. This probably might be a bit too long for it to show frames. It's quite long. It's a bit hard to see, but you can actually see the end of frame marker there. So it's framing these as complete transactions quite nicely. And we can go into the zoom mode, which incidentally, so I just noticed you can actually adjust the proportion between the full and zoom mode on there. Scroll down to different details. One thing that's a bit annoying is using the knob for this is annoying because you don't have the sort of velocity sensing. So this is just a bit painfully slow to use. So I think some of the times they sort of taken the issue, well, you've got a touch screen, what do you need the knobs for? But if you're used to using knobs, there are a few things, with the detenting and the velocity sensing, which I think could have been done perhaps a little bit better. One nice thing though is you can just flip between these views and change that view and the overall view, whereas a lot of scopes, you go into zoom mode, then to change your overall time base you actually need to go out of zoom mode and back in again, whereas this one you can actually just sort of tap each one. I'm guessing you can you can actually do the stretchy thing on that one. Can we do it on here? I think we might be suffering from this left-hand reference bug here. But yeah, it looks like we sort of can. But say that the zoom window, you can sort of just do that, which is, I think the whole touchscreen thing, it's really about what you're used to, but it does seem to work quite nicely. So for example there we can look at the overall view and then we can actually see our read and acknowledge bits there. The I2 setup is pretty straightforward. There's just SCL SDA, and you've got your threshold auto find. And again, trigger, we've just got start, stop, restart, missing acknowledge, and address and data. So looks like I can actually trigger on a specific device address and data, so that's fairly reasonable. So there's not really much more to say about that. It's just I2C is pretty standard stuff. Just take a quick look at the other options, which are CAN and LIN. Now I don't really know much about either of these. I haven't got any way of generating it, so I'll just look at the what the options are. So for CAN, we've got baud rates up to 2 meg, and for CAN trigger, we've got start of frame, end of frame, frame identifier. So these are sort of address triggers, identifier and data. So it looks like we've got a fairly comprehensive range of CAN triggers there. So I don't really know anything at all about CAN. And LIN, which is another automotive standard, which I think is basically UART with just a bit of extra synchronization stuff going on, and the baud rate on that. It's interesting. Maximum is 2.520161 megabaud. That's a fairly precise thing. It's interesting because I thought it was pretty much the same as UART, but it's only going up to 2 point whatever rather than 3. But maybe that's to do with the synchronization stuff. And for LIN trigger options, we've got start of frame, wake, error, identifier. So again, you've got the same sort of range of options as for CAN. Right, let's take a look at the digital inputs and bus modes. I've got this connected up to this one of these Chinese cheap video wall panels. I'm just driving with my little board. It's pulling data off an SD card using FPGA to generate all the modulation. So the signals we've got here, we've got 4 bits of row count information. So this just counts the 16 rows for doing the multiplex. And then we've got serial clock, latch, enable to enable the data for that bit value and some actual data down there. Again, like on all the other modes, it does have very good control over how we display this. So for example, our heights can be, we've got quite good control over how high we want these. We can move them all up and down as a whole, but we can select individual ones. One nice thing is obviously as they're close together, it gets difficult to select individual ones. So what happens if you press on one and it's a bit ambiguous, it actually gives you the choice of all the ones in nearby. So let's say, for example, that was D4, we want to actually move D4. That's now selected D4, we can see it selected over here, and we can move this around. Now obviously when you're dragging these around, it can end up looking like a bit of a mess. But one nice thing is when you click the size backwards and forwards, it then respaces them, but it still keeps them in the order. So for example, let's say I want to get these rows in order, say these rows are out of the normal order, so I want to take D3, move that up there. The next one would be D0. Move that next to it. So they're roughly in the right order, and again we just sort of click the thing and it will just respace them quite nicely for us. You can assign labels to all the traces. Now when I was first trying this, I sort of was thinking it didn't work, so I wasn't seeing these changing, but actually it does. It actually puts the labels over here, so you've got your assigned labels here, and it still retains the default names. That's actually quite useful because some scopes, when you assign it a label, it actually, you lose the actual channel number information, so it's one or the other. So the nice thing here, we've actually got both. And so for example, if I've labelled up some of these rows, I should label this last one here. If we go to, there are some predefined labels, but because we've got the keyboard entry on the touchscreen, these, on scopes that didn't have a touchscreen, these are actually quite useful, compared to like entering letters using the knobs. But because we've got the touchscreen, we just type it in. So we just type in our label. And on the logic inputs, obviously we can select the threshold. This looks like it's a global threshold for each of the set of 8, which is reasonable. You've got sort of predefined levels and also user levels where you can just enter a voltage from -2 up to +8 volts, which covers pretty much all the range you're likely to want. You can also have adjustable hysteresis, which is interesting. So that would be handy if you've got noisy signals. So in fact, if I set the hysteresis small, because I've got fairly not particularly well grounded, for example, I'm only grounding one of the probes here and I'm not bothering to ground the other ones. So we've actually got some noise, so you can actually now see we're actually getting a few sort of spurious spikes because we've set the hysteresis very low. So that's actually quite a handy facility if you're particularly for, if you're doing not particularly critical, speed critical things. You can just up the hysteresis to get rid of the noise that you've got on there, because it can be a bit of a pain with these logic probes. If you've got to ground every single one, it can be a bit of a pain to do. Right, now let's see if we can get a bus set up for these 4 to give us a row number. So I haven't tried this before, so let's see if I can do it. Obviously, so set a parallel bus configuration. Okay, so how do we we want to not use some of these. Okay, we can select from those. I'm trying to figure out how I can just tell it not to display that, because I'd like a bus with only 4 bits. Oh, here we go, bus width here. So 4 bits. Now our sources, because the way I've probed it, they're not in the right order. Actually, I think I've got a feeling they're in the right order, but I'm actually doing some interleaving, so they're not, the count isn't in the right order. But say because we've got our labels here, we can, so bit 0, we want row 0. Oh, that's a bit annoying. We've assigned our labels, but when we go to the pull down box, it's not giving our labels. That's borderline bug or misfeature. It should be telling us our labels here. That's actually quite annoying. Next one. Yeah, that's actually really annoying. It really should be putting labels on that pull down. So I'd say that's something that they need to sort out. So we've now got our bus display showing the numeric value of that bus. So you can see it's doing 16 rows. So we've got this count, and again, like the other decodes, we can move where we want. We've also got this little bits display, so we can actually turn off our logic input display if we want to. So we've now just got our bus display here, just like all the other options. And so we still do have our little display of the waveforms, and again I'm sure we can turn that off if we want to. So we go to display setup, so we just turn bits off, we can turn that off if we want. But again, that's the nice thing is it keeps them associated with this bus, so that if you move it around the screen, yeah, it all stays in the same place. Whereas if you're doing it with the bus display, you know, they don't move together, so that's quite a nice little feature. But say you don't have to use that, you can just turn it off if you want. Oh, that's interesting. We can also do a table display of this. That's nice. So as well as showing it on screen again like the serial decodes, we can actually now look at all the values that have appeared on that bus and their relative timings. That's really handy. So you can actually take a load of bus data, and again we can save that off. We can show either differences from one value to the next, transition to the next. So that's actually quite a nice feature. It's interesting that there's they seem to have taken a slightly different approach in that, whereas for example on the Keysight the bus is just a standalone mode, it's just a mode to group signals together and display them, whereas they're actually treating it as a protocol decode. So you've got all the facilities that you have within protocol decode, like the table mode. So that's quite nice. The only minor downside, obviously, that counts as one of your decodes. If you're trying to decode multiple protocols, you can decode, let's say, one serial protocol and the bus, but I really can't see that being an issue. You'd have to have a crazily complicated system where you actually needed 2 decodes and bus display and decode at the same time, and you can always switch between them if you really need to. So I don't think that's really a major limitation, but the fact they're treating it like it's a protocol means you do have access to some useful additional features. Something else you can do, this applies to all the protocols, you can actually assign a label to the protocol decode as well, which is quite nice, because if you've got multiple protocols, it's useful to actually be able to tag those to say know which ones which if you had multiple buses or multiple decodes going. One thing I wish this would do is actually have the option to make transparent menus, because quite often when you're setting this stuff up you actually want to refer to what's on the screen at the time. So it would be nice if that would actually sort of push through. I'm not sure, can we actually, no, we don't seem to be able to drag these around to see what we want. So yeah, I'd like the option to actually be able to see what's going on underneath. Yeah, especially because it isn't showing us our user labels in this menu, so that's a bit annoying. That's definitely something that they should do. It's not like there's not space. It looks like they've actually left enough space for the labels. They just seem to have forgotten to actually put them on. Well, it looks like the 2 decode channels aren't quite as flexible as I thought. I mean, it's not a big issue, but I've got this one doing the parallel bus decode. What I wanted to try and do is set up this second one as an SPI, but it's not letting me turn it on, and it looks like it seems like it only can do one type of protocol at once. So for example, if I set this to parallel as well, it does let me turn it on. So it looks like, which is a bit annoying, and it's not the end of the world. It'd be nice to be able to do 2 different protocol types. Let's just see if there's any other limitations on that. And it's also annoying, it's not telling me why it's not letting me do that. Now, it seems reasonable, well, you know, there might be some limitation that you can't do two different ones at once, but, you know, if I try to turn it on, I want it to pop up something and say, look, sorry, I can't do this. Or, and also maybe just disable the other one. You say you know, I want to set this up as because I think you can probably still set it up so you have two buses and you can turn them on one at a time, but it looks like even if this first bus isn't set to decode or trigger, which it isn't, you still can't enable this unless they're both the same. So if I set this one up to SSPI, it will now let me turn this one on because they're both set to the same type. So I think, okay, you know, maybe there's a hardware limitation that means you can't do two different types of decode at once, but please, you know, give me a bit more feedback if I try and it doesn't let me. Actually, I think this is actually a bug because, yeah, I think this might actually be a bug, because if I set, so I've got this bus 1 as parallel decode. If I set this to parallel, enable it, and then change it to SSPI, it does look like it's working. So I think that's maybe a bug in the enable logic. So yes, it looks like it can do, and that looks like fairly plausible SPI decode on this bus here. So yeah, it looks like that's actually a bug. So you can do the bus and SPI decode, it just, you have to work around some sort of bug in this enable disable. So I think if I disable that now, I suspect it's possibly not going to let me re-enable it. So it lets me enable and disable that one. Yeah, it's turned off the other decode, but if I just go parallel, enable, and then change it back to SSPI, it does actually display both. So yeah, there's some bug there with the enable disable logic on the decodes. Right, I've now set it up into the parallel clocked mode, and in addition to the normal bus information, you've got a chip select and a clock input. And this seems to do two things. Firstly, the chip select shows whether the bus is shown as grey or white. So I define chip select here as being D3, so it's high here, low here, high here, and you can see it's sort of dark grey here and a lighter colour here, and if you just sort of shrink it down you can still see it when it's compressed. And I've defined D6 as the clock, so it looks like all it's doing is that instead of just giving a display whenever the bus changes, it's actually giving like a marker on every transition of the clock. So obviously that'll be handy for things like, for example, traditional peripherals where you've got like chip select and chip select and a sort of parallel data bus. So this is just really, the main difference really is just how it displays it. It's just producing additional markers even when the bus doesn't change, because quite often when you're doing a bus decode, if the data doesn't change, sometimes you want to know, well, when ought it to be changing. So just by adding that clock, you're effectively modulating the display, just give these markers to show when the thing is being updated, even if the data is actually the same. And again, say the chip select is just giving you an active inactive type display. So that's quite a nice little feature, and again something I've seen before. Oh, I see. It looks like it's now using the chip select for framing this bus table information as well, so that's potentially quite useful. So for here, for example, here we're seeing this section here is this 020202 and the next one. So basically this is only displaying information when the chip select is active. So we've got chip select active here when we're showing 2, then up here when we're showing 4. Again, we've got that data here, and it's just showing the data as it's basically within the screen field of view. So if we reduce that, again we can actually show all the data. So that's actually quite nice. So we can actually get more information than we're seeing on here, because it's actually splitting into frames and then showing these separately. So we can move this up and down to get more. So we could sort of get a mostly bus display. We don't seem to be able to stretch this at all, but say we can sort of stop that and then save that off. Okay, I think that's covered most of the serial trigger. I just want to take a look at a couple of other aspects, in particular how well it deals with large amounts of data. I just found one other minor issue in UART decode. So this is an 8K packet. It starts with an FF and then the rest is image data, which doesn't include an FF value because I use that for synchronization. And you can just about see a little bit of movement in there if I adjust the intensity. And I'm triggering on an FF byte, so I've set up the UART trigger to trigger only on FF, and I sort of found one minor issue while doing this. If I've got sort of relatively infrequent packets, it's fine, and if we zoom in, we can see our FF data as we'd expect. So it started on FF and then that's our image data and so on. But if we zoom in just on the main time base, what starts happening is that it's actually re-triggering on the same package. I think what's happening is, yeah, if we do a single trigger it still works fine, but I think what's happening is that it's triggering on a bunch of data, and by the time it's ready for the next trigger that packet is still going on, so it's re-triggering, but the UART decoding engine is failing to keep synchronization from one acquisition to the other, so it's seeing data that it thinks is an FF, it's actually incorrectly byte framed, so that it's mis-triggering. Now that's a minor annoyance, but so that, the obvious quick solution to that is, okay, we just add some hold off to make sure it doesn't try re-triggering until after the end of the packet. Problem is, no hold off. No hold off in protocol trigger mode. Hello? That's definitely something that's not good. Okay, so I've now just changed it to an edge trigger with a selected hold off for the packet, so we're now getting a stable sort of packet framing here. So just want to just see how it feels for when we've got quite a lot of data going on. Each of these packets is 8K bytes of data, so we're still managing to decode there. Shrink that down a bit. Obviously at some point we're just going to run out of memory and not be able to decode. So here, it's looking wobbly, and in fact the frames are actually showing red, which indicates we've probably not got enough memory to decode that. I've not quite figured out exactly how this thing treats memory. It does have a mode where you can explicitly select record length, and an automatic mode. If I just set that to 10 megasamples, this seems to be doing basically the same thing. So it looks like it's automatically selected the maximum length for the mode that I'm using. And speed wise, bear in mind that this update rate is this is the rate that I'm actually sending it. It's not down to sort of the thing being slow. So I mean, it's not getting noticeably slower really for that when it's dealing with the format. One of the problems with some scopes is that as you increase the memory depth, the responsiveness and so on starts sort of going down the toilet, but this actually seems to be pretty similar. In fact, if I just take that down to, let's say, 1 megasample memory, so now we're not getting enough samples because I've reduced the amount of memory. So this is updating faster because we're triggering, we're triggering on more packets. So that's not a function of the scope, that's a function of the rate that I'm sending the data. But it still seems pretty responsive and usable, so it doesn't seem to do anything particularly unpleasant when you increase the memory. One thing I did notice though, just on the subject of memory and acquisition, again it's sort of a fairly unusual facility I've not seen before, is obviously normally you've got sort of normal run and sort of single acquisition mode, but what you can actually do is you can actually tell it to, when it does single, to actually do multiple acquisitions. Now obviously this makes more sense in conjunction with the intensity grading. So for example, if I do single, it'll actually do 4 acquisitions. Now in the context of what we're doing here, that doesn't make a huge amount of sense, but if you're doing something where if I turn that hold off, turn off that hold off, that might make a little bit more sense. I really don't like how they've buried the hold off at the bottom of this menu. That's really inconvenient. So now that we've got the intensity display making a little bit more sense, so if I just set this to, so that's our normal single acquisition, it's always going to acquire exactly one sample. I can go to, is that related to the number of memory samples? Yes, that's related to the number of the memory segments. So if we have a longer memory, we've got fewer samples, but we'll leave it at that. So that's 1 megasample memory. So, but what I can tell it to do is acquire, let's say, 8 samples. So when I hit single now, it actually requires 8, and obviously we've got the overlapping. The protocol decode doesn't really make sense here, but we can see with the intensity grading, we can actually acquire a specific number of samples, which I think is actually potentially quite useful. Maybe if you're actually come think of it, in conjunction with the color display mode, that actually could be useful, so that you can do a fixed number of samples and produce a color histogram based on a known fixed number of samples. So for getting statistical information on eye patterns, that could actually be quite useful. Right, so I think I'll leave it there. So the protocol decoding, it's got some interesting features. The screen layout in particular, it's really nice. The fact you've got very good flexibility on the screen layouts. Few minor bugs I'll post in the description if I get any feedback that those have been fixed. But I'll obviously report all those back to Rohde Schwarz. We'll see what they say about that. But I think the protocol decoding facilities are pretty comprehensive. They are more flexible and comprehensive than most other decodes, and in particular the screen presentation is quite nice. And say once they get this UART framing issue sorted, that'll make that really useful. I still think cost-wise they are expensive. If you really need this to do a job, then I'm sure that they would easily cover their money. But hopefully we're going to see maybe some promotions with options thrown in here and there, because that's what a lot of the competition are doing. So. But certainly, as you see maybe in my previous video about decodes, serial decodes are definitely useful for more than just protocol decoding. They're a very useful real-time debug tool as well, so definitely worthwhile. And this scope does a pretty good job. I think probably my only sort of reservation is that it only goes up to 3 megabaud, which obviously for a lot of people that won't matter, but for me personally it would actually be a fairly significant issue. But the fact that the SPI seems to work at like 50 megahertz, hopefully they can maybe add some higher baud rates to that.